So that's why in classical mechanic, you learn about two kind of formulation, the so-called Lagrangian formulation and the Hamiltonian formulation. And this, the classical mechanic, bring you to quantum mechanics, where Hamiltonian is almost everywhere. But Lagrangian here give you to quantum field theory. Okay. And then this quantum mechanics not enough. You also go to later to relativistic quantum mechanics and so on. So the connection between here, going here, is relativistic quantum mechanics. To connect, so you have to include relativity here to go to quantum field theory. So the quantum field theory all formulated in Lagrangian methods. So in so-called all these forces, the EM, the weak, the strong, and unfortunately gravity cannot be formulated so far by some Lagrangian density. So, but before I write any form of Lagrangian density, it's better for me to say that you can also formulate high energy physics in terms of Hamiltonian, but more difficult. So Lagrangian density is the easiest. You all know that once you know the, and then you want to model any interaction or any behavior of particle. If you look at the classically, you will see that Lagrangian is the easiest because you have once you know the Lagrangian, or you call it model the Lagrangian, then you put into the Euler-Lagrange equation, and you get the equation of motion of the particle. So the Lagrangian is the easiest, and that's why quantum field theory is based on that. So you minimize the Lagrangian density, and you get the equation of motion of the particle, and from there you know what is conserved, what are the particle involved, and so on. Now, whereas if you use Hamiltonian approach, usually you have to know the wave function, and then you, in the Lagrangian case, you don't have to know the wave function. But in the Hamiltonian, you have to know the wave function, and then the Hamiltonian act on the wave function of the initial state to give you the final state, and so on. So, so you have to know the wave function, or you have to model it. So that is the difficulty. Now, so in high energy physics, this is the and QFT involve Lagrangian density. Now, just to, so we don't, so far, I mean, I will introduce to you some Lagrangian densities for all the different forces, but let's not go too far yet. Let's just concentrate on at a lower level. We work on Hamiltonian first. Okay. So basically, when you in general, this in high energy physics, usually you start with experiment first. Okay. Of course, there are times when theory comes before experiment, but most of the time, so the first thing you measure a kind of conserved quantum number. So this is the first thing that you do, and then you determine the symmetry. And then you define the form of Hamiltonian. And then you work backward to predict whatever. And then you work backward here to predict whatever extra has been left by the Hamiltonian. For example, so you have mu minus decay into a mu minus E minus mu E mu. I'm lazy to write the plus, so I hope this is a new way of writing. Okay, meaning a muon decay into a electron, and antineutrino electron, electron neutrino, and muon neutrino.